Okay, now we're recording. Um, now, now and then, with homework problems, it seems like there's a uh, misconception about which problem is actually assigned. So I want to make sure that we're all looking at the same version of a book, the one that I sent to the class. Um, so. Um, So the book version that I am going by for purposes of assigning problems is the one that was emailed to all of you on the day I submitted the book to the publisher, January 29th. I had sent one like on the first day of class or so, but then that had been modified. So then I said this was the final version. So. So make sure that's the one you're looking at. I no longer post it on the site because it's something that's supposed to be published and therefore paid for by somebody, just not you. Just to avoid any confusion about which problem it is. Okay. So I totally forgot. What is the new section for today? A new method, well, new to you guys, for finding roots of equations, general nonlinear equations. Of what we're going to see today, well, depending on how far we get. And what we'll see is that, unlike bisection, which is guaranteed to work if you give it the right situation, the other methods that we'll see in this chapter can fail, but we can have some idea of when they will and when they won't. All right, so I'm not sure if we'll get through all this today, but I have budgeted to spend today and Tuesday's class on this. And if we end up getting through all that faster, there's more methods in this chapter to cover anyway. See if we can get in before spring break. Okay. Well, at least somebody's getting a call, just not me.
No, it was just a
yeah.
Just
Yeah. And actually, since this is a math class, let's talk about number sense out in the real world, because a lot of people don't have any, and it makes it very difficult to communicate regarding numbers. And for example, the very person at the car dealership who's supposed to be calling me and is not, said she would call in a few minutes. It has now been
Days.
at least 10 and counting. The airline industry is really bad about this. You're on your plane, you're waiting to go, and they tell you that there's a small delay because some light bulb won't turn on. And in a few minutes, we'll get going. And by 15, by few, they mean like at least 15, maybe 30, maybe infinitely many. So they need to work on that. Because to me, few means really few, like 3 to 5. Yeah. So, but the more egregious example was with this car dealership. Same person who's still not calling me back told me that we need this one part that's $9. So I asked, okay, so what's the total going to be? And she said, well, they won't include that yet. So it'll just be whatever she tells me, plus, and I quote exact words, plus a couple dollars. I said, is it $9? So yeah, a couple dollars.
No.
Yeah. So,
You're like, all right, I'm just going to give you that couple.
yeah. So, so I'm thinking like, oh, so you just added 4.5 couples to the bill. Yeah. So, this is what it's like out in the world. That people have no sense of these things, even what words are used to describe numbers, and so it's up to us to deal with that. And those of you who plan to become teachers, especially, please help with this. Well, okay, we're not going to listen to you, but
It's true, they won't.
but
You can literally yell at them.
that's true. You can yell at them.
You
Yeah.
can whisper, they won't listen. You can write it down, they're not going to read it.
Mm-hmm. But if you yell at them,
They
yeah.
still don't.
Okay.
They just go, why are you yelling?
Yeah. Okay.
No, but I do that when they're sleeping.
What?
I got permission to throw expo markers at one particular child. That's hilarious.
Permission, like from a
The
parent?
dad was like, girl, if you need to throw something harder than an expo marker, hit him with a stapler.
Oh, okay. All right. Well, there's something that can work in those teaching methods classes.
Well, his dad teaches, his aunt's the person that started the school. His mom teaches there.
Yeah.
He's a senior.
Okay.
He doesn't need to be sleeping.
Okay. So, all right. So, what is fixed point iteration? So, we're still trying to solve a general nonlinear equation, but the way we will solve it is we're going to solve an equivalent equation that's in a different form, as x equals g of x. Now, how we rewrite f of x equals 0 as x equals g of x is actually a significant part of the problem here. That there's more than one way to do it. Not any way that we could is necessarily going to work. So I'll give an example of how we could easily take any equation f of x equals 0 and rewrite it as x equals g of x. You could say x equals x minus some function phi of x times f of x, where this function phi, or I should say 5x, is non-zero. For example, if you choose it to be a constant. So that way, so this whole thing on the right side is your g of x, because if f of x equals 0, then all of this will go away, and you'll have x equals g of x. And that's our typical framework for how we're going to transform this equation to this equation. But now I need to explain why would we even do that? What's the point? And the reason why is because once it's in this form, we have an extremely simple method for actually solving the equation in its new form. So, okay. So how you solve x equals g of x is first we choose some value, an initial guess. And all the methods we're going to see in this chapter from this point on will require an initial guess, or sometimes two initial guesses. Then, in a loop, and this loop will keep going until we've achieved convergence. Okay. All we have to do, this is a very short algorithm. We get our new iterate by plugging the old one in to G. And that's it. That's the whole method. You keep plugging in your old x into G to get your new x. As you do this, you're checking for convergence. So I've left that part out of the actual code. So a convergence might mean, for instance, the difference between, or just absolute value, the difference between two iterates in absolute value is less than some chosen error tolerance. So if you see that once the difference between them is that small, then you can conclude, okay, like for instance, tolerance might be 10 to the minus 8 or something. Then you can conclude that the sequence of iterates really is converging, and so what we can say here is, if this algorithm is convergent, then we can say that xk is converging to a limit which, as I have been doing, I'll call it x star. Such that x star is equal to g of x star. So a point like this, you can plug in a g and get so the output is the same as your input. So we say that x star is a fixed or stationary point. You can call either one. So a fixed point or stationary point of G. And that is why this process that I've just described here is called, and my apologies if you did not leave space for this in your notes, fixed point iteration. Okay. So that's the whole algorithm right there. Now it seems like, okay, what more is there to talk about? Turns out there's a ton more to talk about with this method, as simple as it may seem to be, just because we want to have some idea of when it works and why it works or why it fails. Okay. Now, so as I've written here, this point can be called a fixed point. It can also be called a stationary point. Where have we seen the term stationary come up before? Recently. Very recently. Yeah, stationary iterative methods for AX equals B. Because, let's see, okay, I won't write it here. Nope, they still haven't called. Shocker. So with stationary iterative methods, those are a form of fixed point iteration, just working with vectors instead of a single numeric value. So you have xk plus 1 is equal to m inverse n xk, with vectors, plus b. So all of this is g of xk. And we also saw that this converges if the norm of m inverse n, the iteration matrix, is less than 1, and it also converges if and only if the absolute value of the eigenvalues is less than 1. So we're going to have a similar condition for convergence when it comes to the fixed point iteration we're seeing today for a nonlinear equation. But here, this is a linear equation, system of linear equations, so things are a bit easier to analyze in that case. All right. So now that we have, dang it. Okay. Okay. So now that we have an algorithm, I'll actually step through an example of it. And we can see it working and not working. So as an example, we're going to solve the equation f of x equals 0, where our function f is equal to x plus natural log of x. Now, it turns out it's actually fairly easy to show that this function has exactly one root. So first, to explain why it has a root at all, well, this function is only defined for x strictly greater than 0 because of a natural log. Because the limit as x goes to 0, you can't plug in 0, but you can take a limit as x goes to 0. What happens to log x, natural log of x, as x goes to 0? What does it become? Anyone remember that from calculus?
1.
The log of 1 is 0. What? No one? Not even the grad students?
When x tends to 0,
Yeah.
I mean,
Isn't there an asymptote?
There's an asymptote, yeah. But is it going to what?
it's going to the y direction.
It's going negative infinity?
Yes.
I don't think it's
Yeah. Minus infinity. Yeah, so in fact, yeah, whenever x is less than 1, natural log of x is negative. So as you get closer and closer to x equals 0, you're going to get more and more negative values. Okay. On the other hand, what is the limit as x goes to plus infinity? How does log x behave? No. Yes. Plus infinity. Natural log of x, this key would have come up like in Cal 3, for instance. I know, very traumatic class, but it's one of the most slowly growing functions, but it still grows. And then, of course, as x is going to infinity, then the x is going to infinity. Okay, so in other words, f is assuming both positive and negative values. So what you could do is you could find an x for which f of x is positive or negative. So actually, I'm going to go ahead and create this function in Matlab. It's kind of annoying in Matlab. If you want to use natural log, you would say log x. You think ln would be more intuitive. If you want to use log to base 10, it's log 10. So it turns out if you just try plugging in values, you have f of 0.5 is negative, so minus 0.1931. And then if I plug in x equals 0.6, it's positive. So it's 0.0892. So now we know not only the solution exists, it'll exist in this interval. So between 0.5 and 0.6, So we could do what we did last time, use bisection, and eventually you would get a solution. But we like to see if we can get it a little faster than that. Okay, so now we know a root exists in this interval. Actually, the open interval is 0.5 to 0.6. Okay. Now, I can also say that this root in this interval is unique. In fact, it's the only root on the entire domain of f of x, for all positive x. And the reason why is by looking at the derivative. What is a derivative? What? 1?
1 plus 1 over x.
Yeah, 1 plus 1 over x. All right. Now, x has to be positive. So what can we say about this derivative in terms of its sign?
X has to be positive, it's gonna be positive.
So this has to be positive for all positive x. Now, when a derivative is positive, what can we say about the function?
It's increasing.
Always increasing on its entire domain. So, we know it has one root, it cannot have two. Because when a function that has a derivative on its entire domain has two roots, then by Rolle's theorem, its derivative is 0 somewhere in between. It literally is the theorem that says what goes up must come down.
Yep.
So that's what Rolle's theorem says. And since the derivative cannot be 0, so really, so by the converse, no, it's not the converse, it's the contrapositive of Rolle's theorem, I don't feel like writing out Rolle's theorem. It's in the appendix of the book, Appendix A. I will draw Rolle's theorem. The function has two equal values at two different points, A and B, and it's continuous and differentiable. Then its derivative must have a 0 somewhere in between. There has to be a horizontal tangent line. So this is a graphical depiction of Rolle's theorem. So the contrapositive says if a derivative is non-zero on a domain, then f cannot assume two different values. No. F cannot assume the same value twice. That's what I really meant to say. So in other words, it cannot be equal to 0 twice. So it cannot have another root besides this one that we know of in 0.5 root. So 0.5, 0.6. Wow, my brain is really going. And I still haven't gotten a call. So. All right, so we like to use fixed point iteration. That's what I'm going to do now to try to find this root in this interval to high accuracy. Okay. So, I want to take this equation, x plus natural log x is equals 0. I want to rewrite it in the form x equals g of x. So, what is the simplest choice possible for g of x? That's equivalent to this equation. In other words, I'm manipulating this equation. Yeah, negative natural log of x. So I can just take this and move it to the other side. So we're going to solve x equals minus natural log of x by fixed point iteration. Okay. Now, I need to choose x between 0.5 and 0.6. We need to stay within that interval. So that's what I'll do. So I'll make a little chart here. And I'll start with a midpoint of the interval. I go 0.55. So if I go ahead and make a sheet here and put this function in Matlab, minus natural log of x. So if I start with x equal to 0.55, what I get is I'll just use 4 decimal places, 5978. So heading over towards the very edge of that interval. So what you do in fixed point iteration is once you get a value of your function g of x, now that goes down here and that is the next input. So if I put that in, I get starts bouncing back towards the other side of the interval, 0.5144. And then I do that again, and I get something very discouraging. It goes outside the interval. So I plug in 5144, and I get 0.6647. So this is a rather negative development. By section, this would never happen. You keep taking midpoints of intervals, and you just stay in the interval you started with. You have a 0.5, 0.6 in this case. So we're getting values outside the interval, then this is not a good sign. If I were to keep going, I won't write on the board necessarily, but if we keep going outside the interval, it's getting further and further away. And in fact, end up taking logs of negative numbers, which are complex. So in other words, the method failed. So it gets a lot worse from here. So what went wrong? It turns out that we have a bad choice of g of x. Now, right now, we don't know what constitutes a good choice or a bad choice, but we know that this isn't it. So, is there some way that we could change this equation so it's still equivalent, but for which fixed point iteration will now converge? And when you have a bad g like this one, in some cases it's actually a simple way of fixing it. Because minus natural log of x is a decreasing function. Its derivative is minus 1 over x. So a function like that has a non-zero derivative can be inverted. So if I have x equals g of x, and suppose a function g is 1 to 1, at least locally, like in the x's you're considering. Here's what you can do. I can apply the inverse function to both sides. And what will happen is g inverse of g will cancel out and give you x. So now you have a new equation. So if x is equal to g of x, then x is also equal to g inverse of x. So if g of x failed, maybe g inverse of x will succeed. Now, to get g inverse of x, what you do is you solve the equation y equals g of x for x, which is now going to be g inverse of y. So you're just isolating the opposite variable. So in this case, we have y is g of x, which is minus natural log of x. So who could tell me what x is equal to? So if you take this equation and isolate x. Wait, what?
You said e to the exponent.
What?
Minus y. Yeah, because you move a minus over to the other side, exponentiate both sides, there you have it. So now, Okay, so now we're going to try again. Fixed point iteration with this G. All right. So x is equal to e to the minus x. So this is your new g of x. So now I'll do the same kind of chart. I'll start with the midpoint of the interval where I know there's a solution, the 0.55. Wait, that's why I put down here. Okay, so now I have g is e to the minus x. Okay. All right, so g of 0.55 is 0.5769. Okay. At least we're staying in the interval. Hopefully we will continue to stay in the interval. Okay, so then I move that down here. 0.5616. All right. Better. The iters aren't going all over the place. And 0.5702. No, 5703. Forgot to round. Okay. And then 5654. Okay, so there's a much tighter grouping here, at least. Do one more. Okay. 5682. Okay. So it seems like it's 0.56 something. So I'm not going to write down any more in this chart, but if I just keep going in Matlab until it stops changing, and okay, so x star, at least to 4 decimal places, is 0.5671. So it was already in that neighborhood, at least. So in this case, it succeeded. Okay. So we can see that there's, when it comes to fixed point iteration, there are good G's and bad G's. But still, we don't have any way of telling the difference between them. So we need some sort of criteria to know in advance, like before we go to computational expense, whether a certain fixed point iteration is going to work. Because for any equation f of x equals 0, chances are there are many ways to rewrite it in the form x equals g of x. So you want to have something to go on as to how you might go about doing that. Okay. All right. So to try to get a handle on that, okay. We're going to do a little bit of very rudimentary error analysis. Then we'll step back to larger questions of like the existence and uniqueness of fixed points. Okay. All right. So suppose we have a sequence that fixed point iteration produces. Or at least suppose it at least has a limit, x star. Now, if I look at the error, look at xk plus 1 minus x star. Now, I'm going to write this in terms of g. Well, xk plus 1 is g of xk. And x star is equal to g of x star. Why? Because x star is a fixed point. So x star and g of x star are interchangeable. Oh. That's not the car dealership, that's my wife.
She's calling about the car dealership though.
Okay,
That's probably what it is.
Yeah.
You wanna come talk to her?
fine. Hey. Oh, picked up too late.
Let me just text her real quick.
Okay, yes, go ahead. Yes, no faculty meeting tomorrow. Wow, this day's just getting better and better. Okay. Oh. I know. Oh.
Stretch that far. This video's gonna go viral just because I'm being weird. Why screen? Why?
Oh, did you tell her?
Yeah.
Yeah, because she just texted me and says, dang. I guess she must have realized that I was in class. Okay. All right. So now,
She needs you to call her.
like now,
She said, have him call me if he can.
did you tell her that we're in class?
No. And now.
Okay. That's what I thought you were doing in the first place.
Nah.
Okay.
I want you to talk to her. She's a lovely lady. This is all being recorded on our YouTube video.
Okay. All right. Well, we'll see what happens. Okay.
She probably,
What?
she probably thought that we were just meeting or something.
Oh, okay. Yeah. Anyhow, so what you can do with this is I can write this as g prime of some value, which, well, that's the Greek letter c, also known as squiggly.
Ooh, that's what I call it. Squiggle. Weird squiggly.
Yeah. Times the difference in the x values that are plugged in. This is, what I've done here is use the mean value theorem. Another item that for everyone in calculus one forgets, which says that if f is continuous and differentiable in an interval, then the average rate of change is equal to the instantaneous rate of change at some point c in between. So all I've done here is just a rearrangement of that. Okay. So, but the thing is, this is the error after k plus 1 iterations. This is the error after k iterations. So new error, old error. Now we saw something like this with stationary iterative methods. That we want the error. We want to make sure that the error decreases from one iteration to the next. So, so what needs to be true of this to make sure that the error decreases? And keep in mind that this point is between x star and xk. So what should be true of g prime to make sure that the error actually goes to 0?
That should be less than 1.
Yeah.
Yeah, shit.
All right. So, so we have convergence if g prime in absolute value is less than 1, at least near x star. So that way you can have some assurance that the error is going to be shrunk from iteration to iteration, and so it keeps shrinking all the way down to 0. Okay. Now this is similar to the condition from stationary iterative methods for ax equals b. We had the error from the old error being multiplied by m inverse n to get the new error. So the norm of that matrix m inverse n had to be less than 1. So, and it's the same kind of condition right here. So in fact, that m inverse n is actually the derivative of that whole iteration. So really, these conditions are saying pretty much exactly the same thing. Just that one is for a scalar value, the other is for a vector valued function. Okay, so this gives us an idea as to what kind of g is going to work. So now let's put this back in the context of the example that Alice is doing. Okay. All right, so if this function has failed, so if g of x equal to e to the minus x, it succeeded. Now let's take a look at the derivatives. So in the case where, so here in the first case, g was minus natural log of x. So in the so g is equal to minus natural log of x. G prime is minus 1 over x. But x, we were confining x to an interval at 0.5 to 0.6. So what can we say about g prime on that interval? What kind of values are we getting? Do we plug in like 0.5 or 0.6? What's g prime of 0.5? You guys can do that in your head.
Just 0.5.
Yeah. What? No, g prime of 0.5. Negative 2. Yeah.
Negative 2.
Yeah. Greater than 1 in absolute value.
Right.
So we have, so on this interval, g prime is greater than 1. So with that in mind, no surprise that it failed. Okay. On the other hand, with the other g of x e to the minus x, so g prime is minus e to the minus x. Now, when we have a negative exponent for exponential function, then the value is going to be less than 1. So on the interval 0.5 to 0.6, absolute value of g prime is less than 1. And sure enough, it succeeded. So this is a significant condition that we want to make sure that g has a small derivative on whatever interval we're considering where there appears to be a solution. Now, this criteria can also explain why, if you have a bad choice of g of x, why changing to the inverse function is a good way to fix it. Because the derivative, I've always found this to be a very useful differentiation rule, except I'm not even sure that we teach it. The derivative of the inverse function. Actually, just for fun, I'm not going to just write it down. I'm going to derive it. So G of G inverse of x is equal to 1. So G and the inverse cancel each other out. No, that's not true. It's equal to x. I was thinking ahead because I'm going to differentiate this. So if I take the derivative of both sides of this is G of G inverse. So what rule do I have to use to take a derivative? Chain rule. Yeah, function of a function. So G prime evaluated at G inverse of x times the derivative of G inverse is equal to 1, differentiating both sides. So now I can just rearrange this and solve for the derivative of the inverse. So the derivative of the inverse is 1 over the derivative of the original with G inverse of x plugged in. So this is why if I have a bad G, I just take the inverse to get a good G. Because if G prime is greater than 1 in absolute value, I take the inverse and I'm going to take a reciprocal of a derivative. So values that were greater than 1 are now going to be less than 1 in absolute value. So that's why this technique works, to fix a bad G. Now, yep, been almost an hour, still no call. Oh, well, did you tell her what happened? Or?
She's saying that she can see if she
Okay. Because when I talked to the person at the dealer today, I reminded her that she did not call me that back the day before. Brushed it off.
The car's ready.
It is. Okay, good.
You know how much?
It's
a couple dollars.
Yeah. I should already know, but it is okay. Yeah, that's a lot more than.
$9?
Yeah. So, in case you're wondering, the amount I was quoted the other day was $730, and this is.
That $9 grew exponentially.
It's now $8.48.
That is not $9.
Yeah. So yeah, I'm a little miffed about that. Okay. Oh, I need this back.
$90.
Yeah. Okay. Well, that'll be a nice follow-up to yesterday's angry Facebook post.
You have to be ready to leave at 5:20
Okay.
because they stop pickup at 5:55.
Okay.
So it's my job to make sure that you are out the door.
Out the dough?
Out the door.
Okay. All right. Well, that means that you all scram after class.
You can just let us out at 5 instead of 5:05.
Okay.
And that'll give the computer time to load.
Yep.
You could go now and try to make it
Yeah.
You're so helpful. Okay. All right. Okay, so now I think there's still technically 20 minutes of class left.
I would like to say that we probably covered more than most normal teachers cover in an hour and 15, so I think you're doing.
Now that you've said that on YouTube.
I mean, true is true.
What are we covering?
Cats.
Light bulb.
Let's go, here's covered.
Hand turkeys.
How to write 1 through 10 in Chinese.
Oh, right, of course. Okay. So existence and uniqueness of fixed points. So first, existence. We have a theorem which, actually, I'm going to assign to prove in the homework, but is not. It's easier than proving at the inverse of a lower triangular matrix is lower triangular. I'll put it that way. Called the Brouwer fixed point theorem. And what that says is that if a function g is continuous on a closed interval a, b, and when I would say this way, I feel like it ought to be intuitively clear what I mean, but apparently it's not, so I'll just write it 2 different ways. G maps the interval AB into itself, into AB. Because that's what a function does. It maps points. It maps x values into y values. So, but if this doesn't make sense, what I mean by that is if x is in AB, then g of x is also in AB. And so under these conditions, if g is continuous and satisfies this condition, then g has a fixed point. In the interval AB. There may be more than one, we don't know. This only assures existence, but we know that there is at least one. And this can be proved without much difficulty using the intermediate value theorem that came up with bisection. So just because...
Oh, I'm sorry, can you spell the, whatever kind of fixed point theorem is?
B-R-O.
Oh, B-R-O-U-W-E-R.
Thank you.
Yeah, but just because a theorem has got someone's name on it doesn't mean it's hard to prove. Although it usually does mean exactly that. But still working on the Lambert's theorem, whatever that means. Okay. And actually, I'm gonna see if I can draw this situation. All right, so draw an interval AB and try to make it to scale roughly. So this is y equals AB. So what I need to do is, when I draw a graph of a function on AB, I need to make sure that if the x values are between A and B, that the y values are also. So it could be, for instance, something like that. So that qualifies. And if I were to also draw a function, f of x equals x. All right, so this is y equals g of x, and this is y equals x. Sure enough, they have an intersection. So this is a fixed point x star. Now this particular function happens to have only one fixed point. It is still possible for there to be more than one. I'll address uniqueness in a little bit, depending on how much more we goof off. And hopefully I can get this picture right. I'll be very upset if I don't. If I pick some point in this interval, so I'll call this my initial guess, x naught. So what happens is, I take this x value, and I go up to the function. So I go up to the graph. So this right here is g of x naught, but that's equal to x1. So here I have x1, my new guess, but it's a y value when I really want it to be. I really want it to be an x value. So what I'm going to do is I'm going to basically transfer this y value to be an x value, and the way I'll do that is I'm going to draw a line over to the graph of y equals x, because now this is x equal to x1. Because I'm already to correct y value, I want the x value that goes with it. Okay. So now to plug this into G, I go along this vertical line to the graph of G. So this right here is G of x1, which is x2. Now, I need to change this y value to an x value. So now I'll go from here over to the line y equals x. And so this is x equal x2. And then I'll go down to the function. Unfortunately, this graph is not very well drawn, so it might kind of mess up. Because it's supposed to spiral inward. But if my graph is off, then it won't work. So I'm going to cheat. I think my graph is off anyway. So, okay, so really x2 should be over here. Okay. So now I plug in to the graph to get x3, change it to an x value, plug it in again, and then change it to an x value, keep plugging in. Now it's working. And I'm converging to the fixed point. Right. So that's a graphical depiction of fixed point iteration. That there is a fixed point if the function g maps the interval ab into itself. And you see how fixed point iteration works, that y values become x values, and we just keep plugging in to g. So if you were to plot your iterations in this manner, then you get this nice picture here. As long as your graph is to scale. Okay. All right. Now, all right, the last thing I will talk about is uniqueness. And for that, I need to make a definition. So function f is said to be Lipschitz continuous on an interval, I assume a closed interval. Okay. Yeah. On the interval AB, if it satisfies this condition, f of x minus f of y, absolute value, is less than or equal to some constant L times x minus y for all x and y in AB. Now, any Lipschitz continuous function is also continuous, not necessarily the other way around. So this is like a stronger form of continuity. And the constant L is called the Lipschitz constant. Okay. Now, if f is differentiable, on the open interval AB, then we can say that f of x minus f of y is equal to f prime at some value in between times x minus y. But that is less than or equal to L times x minus y. So this would tell us that f prime of C is less than or equal to L. Now, really what this tells us is if this does not necessarily mean that the derivative itself is bounded on all of AB, because we don't know what C is. We know C is some point between x and y. We don't necessarily know, but it covers the whole interval. So what I can conclude from this is if f prime is bounded by some constant L on AB, then we can say that f is Lipschitz continuous on AB, and L is a Lipschitz constant. So in a case where f has a derivative, that's something we can conclude. Now, fixed point iteration itself does not require that the function have a derivative. I mean, in our examples it does, but it's not absolutely necessary. It definitely has to be continuous, though. Okay. So, with the notion of Lipschitz continuity, I can state, and this is where I'll quit, the all-important, still recording? Yes. The contraction mapping theorem. Okay. So this has to do with uniqueness of a fixed point. So the contraction mapping theorem says that so if we have these conditions, G is continuous on AB. Second, G maps the interval AB into AB. Now, these are the conditions that we already have for the Brouwer fixed point theorem. So that alone ensures existence of a fixed point, but now we're going to pile more conditions on top of it. If G is Lipschitz continuous, on the interval AB, and there's a Lipschitz constant. Well, Lipschitz continuous means there is a Lipschitz constant. L has to be less than 1. Okay. Then, so another way of putting it, if G is Lipschitz continuous and Lipschitz constant less than 1, G is a contraction. I hear packing up, knock it off. I'm the one supposed to get out of here in a real hurry. So G is a contraction on AB. So if those conditions are satisfied, then finding the conclusions, G has a unique fixed point, x star, that's in the interval AB, and fixed point iteration is guaranteed to converge. What's more, it converges for any initial guess x naught in AB. So if you've identified an interval where G has a fixed point, and you're able to establish Lipschitz continuity with a Lipschitz constant L less than 1, which also means if the derivative is less than 1 in absolute value on the interval, then we are assured that fixed point iteration will work. So in that example I did with a g of x equal e to the minus x, I could show that that function g does in fact satisfy all three of these conditions, and sure enough, fixed point iteration worked in that case. So a bit more stringent conditions than we had for bisection, where all we required was continuity and a sign change. But at least we have something here. And in fact, fixed point iteration is used to prove existence and uniqueness of solutions of all kinds of equations. For example, differential equations. The existence uniqueness theorem for differential equations is based on fixed point iteration. So you would have seen that last semester. It worked with contraction, and got awful proof. So really, this is one of the most powerful practical and theoretical approaches to solving equations, is describing it as a fixed point iteration. Okay, and now, I've used about 3 minutes, and apparently I've covered enough. So, just saying. Okay, yes, I really have covered enough, and I have a whole other day for this. So, okay, so we're good. So, and I guess I'm getting in my car.